Hello there, my name is David Cater. In this video, we're going to take a look at sine waves, and we're going to look more into the calculations that are required for us to understand how systems are working. Okay, so here I've got a classic sine wave starting at the origin, and we're going through our positive alternation and our negative alternation, and we're at a full 360 degrees, one complete cycle. Okay, so first thing we need to know is what is the peak of this sine wave. So this is the value right up here. So I'm going to pick a classic value for electricians, and that's 170 volts at the peak. Now remember, this is an AC voltage, but because we're picking a moment in time, we can give it a positive or a negative value. And so this is a positive 170 volts, and that would be down here, we have a negative 170 volts. That's awesome. That tells us that, yes, it is alternating current because we have both a swing of positive and negative voltages and therefore positive and negative currents. All right, so this is, believe it or not, what is present in everyday electrical circuits, 170 volts at the peak. But what we do know is that when we take a meter and we measure it, we're actually only going to measure about 120 volts. So if this is 0 volts and that's 170, then somewhere in here, I'll pick a spot here, somewhere along this line, we're going to have 120 volts. So you can kind of see it's kind of like the average. If our meter was measuring peak, well, peak's only there for a brief moment. So it's probably better for us to understand it as more of an average voltage than it is as a peak voltage, because this is where, you know, we really start to utilize this voltage. It's really the effective voltage. So I said it's the average, but it's not the average. It's really not the average. So what it is, it's called an RMS value. And this stands for root mean square. So that's a mathematical function to do a root mean square. So what that does is it takes this entire sine wave and it squares it. And so I'll just kind of show you what that looks like over here. So we have a positive bump and a negative bump, and when you square a negative, you get a positive value, and that's good. So we get what used to look like this is now going to look like the squared value, but the negative turns positive, so it looks like this. And then after that, we go ahead and we root it, so then we get right back to our original numbers that look like this, but now they're both positive. And then we take the mean of it, and that's kind of like the average. So it's kind of a really complex function for figuring out what the effective voltage of this sine wave is that has a positive 170 volt peak. So it's called the root mean squared, and the function is quite complicated in calculus, but for us, it has been boiled down to a very, very simple application. So all we really need to do is take the peak. You can also call that the max, the Emax. And what we need to do, pardon me, is we need to take that value and we need to divide it by the square root of 2. And that's going to get us the voltage, or the E RMS. Another way to go about that is to multiply it by 0.707, and that'll get us the E, the RMS value of E. Okay, so both of these functions do the same thing. It's just the perspective that you're looking at. So to take a value and divide it by root 2, or to take a value and multiply it by 0.707, that is to do the exact same thing. It's just the way the numbers work out. Both of them are going to get you the value of E RMS. Okay, so when we go ahead and plug it into our numbers up here, what does that look like? So we have our E max, which is 170 volts. We're going to divide that by the square root of 2, and that equals roughly 120 volts RMS. That's exactly what we want. This 120, which is the RMS value, or the effective value that we utilize within this sine wave. Okay? Same thing we could do as if I showed you down here. 170 volts multiplied by 0.707. Multiply, there we go. And that would equal 120 volts RMS. So both of them are going to work. It just depends on which one you kind of choose to use. But that is ultimately what the RMS value in this symmetrical sine wave is. It's taking the peak, dividing it by the square root of 2, and we have the effective voltage. So RMS is really just a synonym for effective voltage. All right. So you may be asking yourself, where does that lie within this graph? Because we know that this here is 0 degrees and this up here is 90 degrees. So it's somewhere in between. We're at 90, sorry, between 0 and 90, we're at 120 volts. And we can see that it occurs here, then it comes around and it occurs here again, and then it's actually going to occur here, and it's going to occur here. So it's a kind of a sort of a safe assumption that maybe between 0 and 90, halfway up, is going to be 120 volts, this effective value. So that would be at 45 degrees. So what we can do is we can actually calculate that to see if that is the truth. So we'll do that, and we'll leave it there. All right, so let's go ahead and see what that looks like. So I have a value that looks like this, which is 170, and I'm trying to figure out, there it is, basically what the height is here that goes from the baseline up to that point at 45. So I'm actually doing just a basic right angle triangle. This triangle right here, the hypotenuse is my 170 volts. So I'm going to draw that here just to show you. So my hypotenuse is the peak, 170 volts. And what I'm trying to do is figure out what is the vertical component from the baseline up to the degree that we're looking for. So I said probably something like 45 degrees. So let's solve for this side. When I look at this triangle, I know it's a right angle. So I have a hypotenuse and I want to find the opposite. So I'm thinking sine function. Sine is equal, or sine theta is equal to the opposite over hypotenuse. So I've got everything I need here. I've got my sine of theta, 45 degrees. I've got my opposite value, the thing I'm looking for, and my hypotenuse. So let's go ahead and use the sine function. Okay, so I'm going to do my peak, which is 170 volts times the sine of 45 degrees. And that's the trig function that we're dealing with here. And when I go ahead and I punch that in, I get, surprise, surprise, pretty close to 120 volts. All right. So that's exactly what we wanted it to be, because it's 120, 120, 120, 120. Every time we do it, this divided by the square root of 2, times it by 0.707, times it by the sine of 45 degrees. Every time we got to 120 volts, which is exactly what our meter is measuring. And that's exactly what the effective value is. So just to kind of go full circle on this, the sine of 45 is equal to 0.707, which is the number we used up here. So that's more or less why it worked out. Okay, so sine waves, lots going on. We want to be able to figure out what the peak is, what our RMS value is, and perhaps any value along this sine wave that we want. Just remembering that I'm going to hit my RMS value here, and at 90 degrees plus 45, 135 degrees, down here, and now here again. And what we want to do is figure out exactly where it all is occurring within the sine wave. All right? So I hope you found this video educational, and we'll see you in the next one.